Okay, sorry guys. Is it better now? Okay, great. So this week we are going to be covering a more challenging topic that's not normally seen in AMC8 and math counts, but it is useful to know. And this is directly relating from what we learned last week, which was modular arithmetic. So let's get started here. So we're going to be learning about Euler's Totient function. And Euler's Totient function is typically written like this. You might see this in several forms. It's called the phi function, or however you want to pronounce it. And usually it's written like a circle with a line through it. And if you want to take that function and plug in a number n, you would write it like this. So, and you can another form of the notation you can see is written up here. And basically what this function does is if you plug in a positive integer n, then it gives you the number of positive integers less than n that are relatively prime to it. And remember that relatively prime means that the GCD of two numbers is equal to 1, which means that the numbers have no common factors. So let's start with some examples. Let's say I give you the number 6. So can you guys count for me which numbers that are less than 6 are relatively prime to 6? Two and three are kind of the opposite of what we're looking for. So we're looking for numbers that don't have anything in common with 6. 2 and 3 have themselves in common with 6. Okay, so the numbers here would actually be 1 and 5. Because if you look at the numbers that are less than 6, you would have 1, 2, 3, 4, 5. And the numbers 2 and 3 are actually factors of 6, which means that their greatest common divisor is themselves. And that it is definitely not 1. 4 here shares a factor of 2 with 6. So the GCD of 4 and 6 would actually be 2 and not 1. So that leaves us with two numbers left over, 1 and 5. So therefore we would write that phi of 6 is equal to 2 because there's two numbers here. So does everybody understand basically how this function works? 4 does not work because the GCD of 4 and 6 is not 1. And GCD means greatest common divisor. So the reason 1 is actually included is because if you plug it into our function GCD of x comma y, you would find that the GCD of 1 and 6 is actually equal to 1. So that's why the number 1 is included. The symbol for the Totient function, I'm not quite sure, but there is a Wikipedia article on it that you could read. But that is kind of semantics, because as long as you understand the Totient function, then you should be fine. So now we're going to go over some properties of the Totient function. So one property is that if you have two relatively prime numbers, which again means that their GCD is equal to 1. For example, can anybody give me two relatively prime numbers? Relatively prime means that those numbers have nothing in common. So there is no number bigger than 1 that goes into both of them evenly when you divide. Okay, so we're going to go with the numbers 2 and 3. So you'll find that because 2 and 3 are relatively prime, the Totient function of 6 is actually equal to the Totient function of 2 times the Totient function of 3. So let's see if this is actually true. Well, we already established that the Totient function of 6 is 2, because the only two numbers that work are the numbers 1 and 5. So can anybody tell me what the Totient function of 2 is? Okay, good. So the Totient function of 2 is 1, because 1 is actually the only number that's less than 2. And it is also relatively prime, meaning the GCD of 1 and 2 is 1. So you have a 1 here. And can somebody tell me what the Totient function of 3 is? Okay, that's also 2. And the two numbers that work are 1 and 2. So you can see here that 2 equals 1 times 2. And in general, as long as you have, it's actually shown up here, but if you can write n as, so if you can write n as the prime factorization p1 to the k1 times p2 to the k2 times all the way to p r, I think that is. It might be a tau, but I think it's r. I'm just going to use r. pr to the kr. Then this holds true. And we've already shown that this works with our example. So can everybody see why this first line here is true? Okay, so let's try another example. Let's try two other relatively prime numbers. Let's say 3 and 5, right? And 3 and 5 make 15. So the phi function of 15 is equal to the phi function of 3 times the phi function of 5. So this equation will be true. And if you actually go out and count the number of numbers less than 15 that are relatively prime to it, you'll find out that this holds true. And this works as long as these two numbers are relatively prime, which means they share no common factors. And in our example in the first line here, you'll see that they extend it to more than 2 terms. So for example, if I had phi of 30, well, you can go and calculate the number of numbers less than 30 that are relatively prime to it. But what you can do is you can break 30 down into phi of, because 30 equals 2 times 3 times 5, phi of 2 times phi of 3 times phi of 5. And these 3 functions are much easier to calculate. So does everybody understand this so far? Okay, great. And note that everybody here is actually muted, so that's to prevent people from spamming with their voices. So okay, so if you actually simplify the equation given up here, then you'll find this formula. So this is a formula that applies for any number n. So phi of n will be equal to the number n times 1 minus 1 over its first prime factor times 1 minus 1 over the second prime factor all the way onto its last prime factor. And note that these things in the denominator actually have to be prime. So this equation would work for any n that's equal to p1 to a certain power times p2 to a certain power, dot, dot, dot. So does everybody understand this formula for the phi function? So basically the phi function is the number of numbers less than n that are relatively prime to it. And this formula right here gives you that number. You might think, why is this useful? We'll actually see later why this is so useful. And first, we're going to do some example problems. Okay, so what is the totient function of 12? So try to experiment solving this problem in multiple ways. So you can list out all the numbers from 1 to 12 and cancel out the ones that have common factors. Or you can use the formula that we learned in the last slide. Well, 1 and 11 definitely work. Be careful about 3 because the GCD of 3 and 12 is not 1 since they have a greater common factor. Okay, so let's get started here. So I'm going to actually go through several ways of how to do this problem. First, we're going to list out all the numbers less than 12. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So out of all the numbers less than 12, we have to remove the ones that have a common factor with 12. So for example, we would have to remove 2 because 2 and 12 have a common factor of 2. So can you guys list out all the other numbers that we would have to cancel out? Okay, some of you are typing good things. So we would have to cancel 3 because it shares a common factor. 4 also shares a common factor. So the GCD, for example, of 2 and 12 is equal to 2. And because this is not 1, we have to take it out. And similarly, the GCD of 3 and 12 is equal to 3. And this is not 1, so we have to take it out. And so on. So we can cancel 4, we can cancel 6, we can cancel 8, 9, basically anything with any 2's or 3's in it, since 12 is entirely composed of multiplying 2's and 3's together. So this has a 2 in it, so we take it out. So after that, we're left with 1, 5, 7, and 11. And the reason that these numbers are left over is because if you try to take the GCD of them with 12, for example, the GCD of 7 and 12, you would get 1 because these numbers are relatively prime. And because there's 4 numbers here, the totient function of 12 would be 4. So that's one way you could do the problem. You could list all of them out and try to remove the ones that don't work. And this gets kind of inefficient for bigger numbers. We're lucky we used 12 here, but if you had a bigger number, like for example, 1,000, this wouldn't work. So let's try to use the formula from the last question. So the prime factorization of 12 is 2 squared times 3. And its individual prime factors are 2 and 3. So can anybody write an expression for the formula from the last slide? So don't forget that that formula is 5n is equal to n times 1 minus 1 over p1 times 1 minus 1 over p2 dot dot dot. So p1 and p2 are the distinct prime factors of the number n. So in this case, the number n equals 12. So can anybody give me an expression for phi of 12? Okay, good. I see one good answer. So on the right-hand side, every time we see an n, we replace it with 12. So our coefficient here would be 12. And P1 and P2 here are referring to 2 and 3, since those are the prime factors. So if you replace P1 with 2 and P2 with 3, you get 1 minus 1 over 2 times 1 minus 1 over 3. And when you simplify this, you get 12 times 1/2 times 2/3, which is equal to 4. So this is a quicker way of getting the answer to the same problem. So don't forget that even though we actually technically have 2 2's in our factorization of 12, our expression 1 minus 1 over 2 only appears once. So we only have one of these factors for each distinct prime factor. The Totient function of a number is the number gives the number of relatively prime numbers to it that are less than or equal to that number. Yes, the p's are all prime factors. So when you prime factorize a number they give you, you would get a certain number of prime factors here. In this case, we have 2 of them, and they are 2 and 3. So when you plug them into the formula for the Totient function, which is basically n times the product of 1 minus 1 over each prime factor, that would give you the phi function of n. So does anybody have any more questions? Okay, so let's move on. So the next question is kind of a troll question here, but what is the Totient function of 1? Well, because if you look at all the positive integers less than or equal to 1, there's only one of them, which is 1. If you take a look at 1, you'll see that the GCD of 1 and 1 is actually equal to 1, which means that 1 works, so there's only 1. So keep that in mind. You probably won't see a question relating to this since it's just you either know it or you don't, but oh, sorry. So in the beginning I said that the Totient function describes all numbers less than a number. It actually describes all numbers less than or equal to a number. The thing is that for most numbers that are not 1, if you took any integer n which is not equal to 1, then the Totient, the GCD of n and n is equal to n. And since n is usually not 1, we never include n in our count of the Totient function numbers. But since n in this case is 1, GCD of 1 comma 1 is equal to 1. And since technically they do share no common factors, we don't we include 1 in our count of the Totient function. So let's try to put the formula we learned to better practice, and let's try this problem. So instead of listing out all the numbers less than 9, let's try to use the formula. So the zero with a line through it is called the Totient function. And the Totient function of any number n is the number of positive integers less than or equal to n that are relatively prime to it. Okay, so 9 can be expressed as just 3 cubed, 3 squared, which means that its only distinct prime factor is 3. So if we apply the formula, then phi of n, which is 9, is equal to 9 times 1 minus 1 over 3. And that's it, which is equal to 9 times 2/3, which is equal to 6. So is everybody kind of getting the hang of how to do this? It is kind of a challenging topic. It's not typically seen on AMC 8 and math counts, but it's useful to know for the future. So, okay, let's try this problem. What is the Totient function of 10, 100, and 1000? So this is like a 3-in-1 problem. Okay, good. I see some correct answers. So let's start with 10. Because 10 is equal to 2 times 5, there are 2 prime factors, 2 and 5. The formula is phi of n is equal to n times 1 minus 1 over the prime factors multiplied together. So in this case, phi of 10 would equal 10 times 1 minus 1 over 2 times 1 minus 1 over 5, which is equal to 10 times 1/2 times 4/5, which is equal to 4. So that's for 10. If you take a look at 100, you'll find that the process is actually kind of similar because 100 is equal to 2 squared times 5 squared, and it has the same 2 prime factors. Remember that the numbers in the exponent don't actually matter. So phi of 100, the only thing that would change here is the first number, since n is 100 now. But because it has the same prime factors, you would write 1 minus 1/2 times 1 minus 1/5. So this would give you 40. And if you do the same thing with 1000, you'll find that phi of 1000 is equal to 400. So this is probably the most important Totient function to remember. If you can remember the Totient functions of the powers of 10, then that's already useful, because a lot of questions will ask you find the first digit or the units digit or the tens digit or the hundreds digit of this number. And whenever you find the digit of a number, you always take it mod a power of 10. So the answer would be 440 and 400. Okay, so we're actually kind of running a little low on time, and I want to get to the theorem. So some of these problems you guys can try for homework. So there's a problem here, and this will be available on YouTube later, so you can always play back the video and try to solve these problems. There's this problem, and there's this problem. Remember, the 1001 is equal to 7 times 11 times 13. So just briefly, I'm going to cover Euler's theorem. So you guys were probably here for mods last time, but Euler's Totient theorem states that if you have two numbers n and a that are coprime, which means the GCD of n and a is equal to 1. Coprime is the same as relatively prime. That means that a to the power of the totient function of n is always congruent to 1 mod n. So does everybody basically understand what this theorem is saying? So that means that when you take the number a, and this works for any a that is relatively prime to n. So there's technically an infinite number of a that could work. So mod is the remainder when you divide it by the number n. So that means that when you take the number a to the 5n, a raised to this power, and you divide it by the number n, you will get a remainder of 1. Coprime means relatively prime, which means that the two numbers n and a share no common factor except for 1. So for example, they're not both divisible by 2 or 3 or 5. So we might not have time, but let's try this problem. What's the 10th digit of 37 to the 41th power? So you guys have less than a minute to do this question. It is a pretty easy question once you really understand how to use the theorem. Okay, so I'm just gonna go really fast here. So 37 to the 41th, when they're asking for the tens digit, they want this mod 100. And since the phi of 100 is equal to 40 and the GCD of 37 and 100 is equal to 1, this simplifies to 37 to the 41 minus 40, which is equal to 37 to the first, which means the 10th digit is 3. You can slow this down on YouTube, but yeah, that's it. I'm going to share briefly these other problems so you can look at them on YouTube. And that's it. So, okay, I hope I see you guys next class. We're probably going to do Vietta's formulas, and have a nice